cavity method result that we had yesterday. Then I want to switch to something which looks different. We'll see the connection, and then I'll get back, hopefully today, to the cavity method. Okay. So we looked at the cavity method in the context for the SK model. I only won't write it again, you all know what this is. And the key was to consider the probability I, that is of Si and Hi, the probability, the marginal probability that the neuron I, that the spin I is at the state Si and its local field is at the value Hi. We wrote it as e to the Si to beta times Si Hi times the probability of Hi, but the probability is computed by subtracting the spin Si. So this was the way we wrote it. This was the full probability at n plus 1, the full system, and this part was the probability of Hi, but the probability induced by the rest of the system without having the spin Si. And again, Hi is here the usual definition, Jij as J. But this is the true marginal distribution. This is the marginal distribution. You can write I here, doesn't matter. The marginal distribution, not the same distribution this, but the distribution of the cavity field. I should say cavity distribution. All right, that's not quite exact. The two crucial steps that we made for continuing to make progress is one is because here the Sj in this case the distribution of Sj is such that the statistics of Sj is uncorrelated with Jij because of the cavity construction. So it's a sum of many terms. It's weak because it's one of the square root of n. The different. Okay, so the two issues which I combined is one is that the different terms here are weakly correlated because the correlation between different spins is order 1 over square root of n, combined with the incoherence of the sum of the Gij, which is uncorrelated with the S, altogether gave us at least an argument. I didn't prove rigorously, but I gave you the argument why we can take, so this was the next step, is now approximation that Pi of Hi, the cavity distribution, is Gaussian. Whenever I write this, I mean, I don't care about normalization. Okay, and this is like minus 1/2 Hi minus the mean of Hi, again, the mean of Hi without the normal the spin I squared divided by 2, let's call it Vi. Vi is the variance of the cavity field. Okay. So these are the thermal fluctuations, the thermal distribution of Hi. So the mean of Hi is the cavity mean of Hi is simply sum over J, Jij, variance of the field. So remember we had J and J prime, J, I, J, J, I, J prime. And here we had delta Sj, delta Sj prime. This was the cavity correlation between two spins, J and J prime. And this is exact because this is just by definition the variance of the cavity field. Okay, but now we made the approximation that this is weak, so the off-diagonal term are really small, and therefore VI ended up to be J squared times 1 minus Q, the diagonal term. Okay, so this is the mean, and this is the value. Okay.
And that's already assuming replica symmetry.
Well, there is no replica here language, but it assumes that there is no problem of, the perturbation of removing spin or removing a spin is making small changes in the quantities, but doesn't protect the system to that extent. So we don't assume this type of assumption, so it would be analogous to replica symmetry, symmetric assumption. Okay, good. So here we have, and now when we put this in this, so now there is a very simple, we can compute this probability just by multiplying exponentials with this. Si is plus minus 1, and so on and so forth, so it's very simple to do this. And what we get is a simple thing. If you, from here, if you combine it with the Gaussian assumption about the cavity field, it's easy to compute, for instance, Si, and this is simply hyperbolic tangent. Hyperbolic tangent of beta of the average of Hi of the cavity field. Okay, that's not good enough because we have to know the cavity field, what are these guys here. However, if we go to Hi, if you use this to compute Hi, then we get Hi is the cavity average plus Vi times Mi times Si. Okay? And therefore we can put everything together and get the top equation, which is that Mi is hyperbolic tangent of beta. Now I'm putting here this, so Hi average is simply the full average of this, so it's average J, J, I, J, and J. Then I have to subtract Vi, which is, actually there is beta here. So minus beta times J squared times 1 minus Q times Mi. Okay, that's top equations. And top, and then, wait, before I answer questions, and then the rest is to compute Q, so one can compute Q by essentially solving this for Mi and computing Mi squared sum over all I. That's one way, but also because of this relation and the Gaussian and the expression for Hi average here, where the mean is uncoupled again to the Jij, the quench fluctuations of Hi is also Gaussian, and therefore we can just say that the equation that I had, the last equation is that Q equals to Gaussian normal distribution times hyperbolic tangent square of beta square root of Q J Z. This is the replica symmetric equation for Q. Yeah, there was questions here?
The equation relating HI and the HI cavity in the
you just compute here. You just sum over SI and integrate over HI. That's it. So I leave it. I leave it to you to do the calculation. No questions. I mean, what the reason why there is SI here, I mean, if you do the calculation, what you get is this plus VI times hyperbolic tangent beta of HI of this term, but then you can, in this relation, you can put it SI. And the hyperbolic tangent comes from the fact that you marginalize over SI and you integrate HI. So that's a simple Gaussian integral. More questions? Okay, good. So, that's nice. There are, in the derivation, there are two, okay, there are several, or maybe two assumptions that entered. One assumption was the weak interactions, and therefore weak correlations, and therefore, and Gaussianity. Now, of course, when there is weak correlations in the terms that build HI in the cavity field, then, and there are many of them, then it will be naturally come to Gaussian. So the two goes together. Two go together. But you can imagine situations that there may be strong interactions, and therefore also strong correlations, and therefore and not necessarily highly connected. So the Gaussianity assumption of HI is even under Kennedy assumption is not justified in this case. On the other hand, it may be the case that the individual terms that make these cavity fields are uncorrelated. Not the terms that build HI, but the terms that build HI cavity fields. And that's often, many times is the case when you have like a random dilute network where the number of connections is small compared to the number of neurons. The connections are strong, but because it's randomly connected, the probability of having path between two spins of 2 degrees of freedom is weak. So this is kind of you can think about it as two extreme ways of generating weak correlation between degrees of freedom. One is kind of highly connected, but weak coupling. Another one is strong coupling, but there are no loops or very small loops, so that most of the degrees of freedom are really not correlated in the cavity distribution. As I mentioned yesterday, even in this case, the fact that they are correlated through the SI will still have to go to the cavity construction. But under the cavity construction, it will consist of elements which are no correlation, weakly correlated, and so on. So we want some more general framework to deal with cases like that, which will have this perhaps as a special case, but will have a broader applicability. So that brings me to a field of approximations of distributions, or marginal distributions, which is known as belief propagation. And the related construction of methods which called message passing. The belief propagation message passing are very closely related. Belief propagation is message passing is an algorithm to calculate marginal distribution. Belief propagation is kind of the final equation that they obey, but I mean I don't really appreciate the difference between, so we will combine it together, but we'll see how it works. Okay, so the formalism is general, in other words, it applies to a general system, but for the sake of notations and for to be more directly connected to what we're talking here, I'll limit myself to a simple case which is more closely related to the kind of Ising models and so on. But the method itself is more general even to that. So we are going to assume that there are n degrees of freedom, again denoted by S. For now, they don't have to be Ising spins. They can be soft spins or something like that. But very quickly, we're going to assume Ising. We're going to apply to Ising spins, but for now we'll make it completely general. We will So I'm going to assume, this is however important, that the probability, the joint probability of all the degrees of freedom in the system, Sn, is factorized. Not in the sense that the probabilities are factorized, but in the sense that the causes, the elements that appear in the probability can be written as products. Okay? So in particular, for pairwise system like the Ising model, it will have the form of product of all links, I don't know, real estate or so whatever, all links in the system that are interacting. We'll call the contribution from the links psi ij, si sj, and then there might be kind of local biases. We'll denote them by phi I, si. And then there will be some normalization. So, in the case of an Ising model, this will be e to the beta jij sij, and this will be e to the beta hi 0 si, where hi 0 is the external bias, external field. Now, we are interested in marginalizing and computing the marginal probability of 1 degree of freedom, Ti Si. So that was something like what the mean field usually is giving us, or the cavity method. So we'd like to have an approximation to the marginal distribution. So what do we have? We have, graphically, we have a node I, and it's connected to many J, and so on. So these are the connections. There is also this local bias. We want to compute we want to write the probability of Si, that's called the belief that Si has the value Si. This marginal, I want to write it as product of contributions from likelihoods, if you want, contributed, but each one of the neighbors, of the elements that connect to it. Okay? So we want to write Pi Si as, again, some normalization, as first of all, the bias, the direct bias, if there is, then phi I Si will be there. And then we want to write the product over all elements J that are connected to I. So I'll write it like this, J in the neighborhood of I, that's my notation. And the neighborhood, of course, doesn't include I itself. So there's no self-coupling. Okay, so this product of all the neighbors of I, and then the likelihoods or the contribution that they contribute to support the assertion, the belief that I, the value I, Si is are the messages that the source J, that the neighbor J sends to I in favor of the spin being in Si. Think about them as kind of messages, okay? So MJI is a message from J to I, and we write it in this form. I'm not saying that, I haven't shown that it can be done. For now, I'm just giving you the algorithm or the frame. So now we want to assume that this is the structure. We want to write now what should be the messages. Okay, what would be them? And the way to write it is like an iterative algorithm. So MJI of Si will either be equal, or you think about it as kind of update rule. And this will be the following. So we are averaging over all the states of the degrees of freedom. So we're summing of all the states of the degrees of freedom of Fj with its direct contribution to the probability. So this would be Fj, Fj, and psi ij, si, fj. Okay, and then the rest of the terms are, I mean, this is not the marginal distribution of Fj. We have to contribute the evidence from each neighbors that it is in Sj. So this will be product of k in the neighborhood of j. But here we are making a cavity correction. We are taking the so now we're looking at the neighbors of j, call it k, right? These are these guys. And these are the evidence that the message that they send that the spin j will be at the position at the state Sj, but we don't want to make the overcounting due to the fact that this is itself affecting those messages. So we're going to make to demand that k is not equal to I.
It has to be the
And
definition.
then we have here M, K, J, sorry, M, K, J, and J. Okay, and this, as I said, you can think about it as a message passing algorithm. Given some initial condition for the messages, at any given time you have your current estimate of the messages, and you use the right hand, you put it in the right hand side, and you put it in the right hand side, and you update all the messages on the left hand side, and you iterate it until it converges, and then once it converges, you plug it in here. So here, I mean, the final beliefs are the asymptotic value of those messages. Okay, there were questions. Okay. So what can we say? So, and again, there is the issue of normalization. Some like to normalize the messages and thinking about them as probability, normalize over the state of Si of the argument. Very often, we just don't worry about normalization. We can, because overall we put the normalization here. This finally, when you talk about the belief or normalize, in practice, when you run these algorithms, you have to normalize because otherwise they tend to grow or to exponentially in time, and, or to go to zero. So it's good. It's a good thing to normalize, but the framework doesn't apply. Okay. So messages are updated in this way, and finally, once you get the estimate of the messages, this is the final expression for the approximation for the marginal of Si. Okay, good. So I'm not. There is an entire industry about the questions of conditions for convergence of the message passing algorithm. And I'm not going in general, if you just have an arbitrary system of this sort, then in general there is no guarantee that it will converge. Not only, so there are two things. First of all, this update rule may not converge to anything, but continue to oscillate and so on. And secondly, even if it converges, it doesn't mean that it gives us some good approximation. It may converge, you may calculate, but it's completely off. So in general, and any other approximation, this can be good, heuristic, can be off. Okay. I'm not going to discuss the algorithm. I'm going to discuss the final, assuming that there is a convergence. So I'm just going to write down the fixed point equations. So basically I'm going to write equal up to normalization. Okay. So this is our set of equations that we want to focus on. There is another, one more thing which will be, okay, I hope I'm building a better board. Okay, one more thing which is often useful. This is to extend it to more than just marginal of 1 degree of freedom. We will see an example why this might be useful. So let me just write, in the same spirit, one can also write the belief propagation approximation for the pairwise correlation, joint probability, and so on. Joint probability of SI, Sj. This will be the direct bias of each one of them, the product of the direct biases, the direct interaction between the pair, and then finally, as before, the messages that the neighbors of Si and the neighbors of Sj send them respectively to support the assertion that they have values Si and J. However, again, we want to extract cavity field. So we are going to do product over K in the neighborhood of I, but not equal to J, and this will be M K I S I, and similarly product over all L in the neighborhood of MJ, but L not equal to I of M L J S J. So this is the belief propagation approximation for the pairwise joint distribution. And again, of course, as we said before, this may be a better approximation, but at least it's consistent in the sense that one can show from these equations that PISI, but again, all these are approximations, but at least PISI is indeed sum over Sj of the approximation Pij of Sj. So at least this consistency is obeyed. Okay. Finally, one question is when this can we think about the messages as these fixed point equations for the messages as coming from some cost function, some minimizing cost function? As I said, it cannot be in general. Are there cases where it is? Okay. Are there cases where this is exact? And under those cases, where can we think about the Mij as coming from kind of the free energy? Now, one can show, I'll give it as an intuition, but one can show that on a tree, in other words, systems with no loops, the belief propagation approximation is exact. basically, the reason, kind of the intuition is that we have this graph, a tree, and now we look at what happens here, and we're looking at the evidence, at the contribution from the other guys to the probability that this has some value. And the way we do it by thinking about the cavity. So we remove this node and then ask what are the probabilities that are induced in this line by the other guys. But because of the tree, if you remove this node, then all this part of the branches are being really uncorrelated. So the messages coming from the different parts of the tree are truly uncorrelated. And therefore you can take them as product. Okay. So this is the intuition, and there are formal proof for that, that the belief propagation on trees, when there are no loops, is exempt. When there are only small fractional probability of loops and so on, there will be good approximation, and so on and so forth. But at least in that case, when they are on a tree, this is an exact thing. So we can ask then, we can then say, well, and for those cases, can I think about this parameterization of the distribution of the marginals as parameterized by these MIs and so on, or by these PIs and PIJs, as a kind of minimization of the free energy, like we did in the mean field in the naive case. Can we do it also here? Okay, so it turns out, okay, so let's try to do it. Let's try to construct a free energy of the belief propagation, which is going to be a function of these parameters, Pi and Pij. Okay? In other words, can we write a free energy for a joint distribution which is constructed by those Pi and Pij, and then by minimizing with respect to those, with appropriate normalization constraints and so on, we will get this equation. That's the question. Okay, so I mean, the problem is that the way we constructed the free energy, remember, we have, in general, this is going to be the energy of the probability distribution of the belief propagation, not backprop, minus P times the entropy of the probability distribution of backprop, of belief propagation. Okay, so this will be the structure. Okay, so the problem is that we just define the belief propagation in terms of those marginals. But in order to compute this, we need to do more. So for instance, this may not be a problem, right? So what is the energy? The energy is just minus log, minus sum of the ij, log of psi ij, of si sj, right? And then minus sum of the I, log of phi I si. This is just by construction. If I think about this as kind of Gibbs distribution, e to the minus, then this would be the case. Okay, so this would be the energy, and the energy will be fine in the sense that they have pairwise terms and margin and single terms. So averaging E, we just need the Pi and the Pij. That's fine. We can just plug in those approximations. Okay?
Your motivation requirement is that the partial derivative of the free energy will be those equations?
Will be those equations. Will be exactly those equations. I want to ask, assume that my distribution is parameterized by the marginals and the pairwise marginals. Okay? What will be the best set of marginals and pairwise marginals that will, best in the sense that will approximate the true probability. That's the question. I want to prove, it would be nice to prove that if indeed you construct this free energy and you minimize it, you will get the belief propagation equations for those guys. That's the goal. Okay, so, and I'm telling you here why this goal is not attainable. And why it's not attainable? Because I have now to construct a free energy of a distribution parameterized by these marginals and pairwise. So the energy part is fine. I can just write, this is the energy, and if I want to average, I just want to, to average this with respect to Pij, and average this with respect to Pi. That's the average energy as a function of those Pi and Pij. That's fine. But now what should I do with entropy? Entropy is the log of the distribution, the joint distribution. But I didn't say anything about the joint distribution. I just told you about the marginals. Okay, so what do I mean by setting marginals? What kind of statement I can say about the joint distribution?
Of the entire?
Of the entire joint distribution, right? I mean, that's what entropy is. Joint distribution of the entire system. I didn't tell you what the belief propagation says about the joint distribution. I just told you approximations for the marginal.
Right, can you explain the problem? It's the logarithm of the distribution. It's again.
This is but this is the full. If I put this, I don't know how to calculate it. This is the true distribution.
Yeah, but you take the logarithm.
Still, it's just the distribution. Okay, I have to average over it. What is the entropy? Average over the log of the distribution. The log of this.
So
when the signs are only hard to compute, or is it possible?
No.
Well, I have to say something more about what do I mean by the joint probability, by this distribution. I have to say something more about that. All right, the answer is, okay, so, right, the entropy. Now, again, you can take the log here, that's fine, but with a z. What do you know about z? It's everything. It's everything, okay? And it's untractable. You don't know how to compute it. Okay, so it's not a good thing. It's not a good strategy. Okay, but the way you can get around it, again, it's not entirely exact, but it's kind of ill-defined, but the way is to ask what would happen if the system would be on a tree. Then I said, well, then, these equations are correct, that's fine, but can I then write the joint probability distribution only in terms of the pairwise, when the system is on a tree? The answer is yes, and actually, it's easy to prove. Just look at an example. So P of f on a tree, the exact distribution is the product over all pairwise P I J S I S J divided by product over all the units on the system times product of Pi of Si, and each one to the power of Ki minus 1, where Ki is the coordination number, the number of neighbors for the site I, coordination number. That you can prove on a tree. So we can pretend that that's what we will have also here, in our case, in general. Okay? We will just use for the entropy this approximation. This approximation. This approximation once you do it, you can write this in just in terms of this Pij and Pj and so on. And I don't know if I have, yeah. And then what you got, when you get is that the entropy S of the belief propagation, I'm going to take it from here to be sum over, I mean, it's easy, right? It's the log of this average, so it's sum over all links, sum over the state, Sij, times average, okay, no, yeah, average over the log of Pij, Sij, average with respect to Pij, and then plus so minus log of this plus sum of the I, Ki minus 1 times the average over the log of Pi. So now there is no z's of things we don't know how to compute. Everything now is a free energy function which has only our Pi's and Pij. This would be a true free energy for a tree. It can be, it will be maybe non-equilibrium. That depends on, you know, the interactions and so on. But for any collection of Pi and Pij's on a tree, the joint distribution must have this. Now, I don't want to get into it, but one can show that, you know, if you take this and take derivatives, you get the fixed point equation for the back propagation. Now you might wonder what happens, what are these Mij and, you know, Mji and so on. Then, I mean, again, under some conditions, Mji and Mij's are coming from Lagrange multipliers of various normalizations and so on. And again, that's not, you know, this is not, it doesn't have the DKF property that we discussed. It's not a cost function in the sense that it's not bounded. It doesn't obey all the Lyapunov conditions that we discussed. But it's a good candidate for the free energy of the system. Again, there are literature on that and a lot of discussions on the validity of this approximation. The reason why I brought it up is because very often when we have approximations like mean field or path equation, we write down equations for Mi equal to this and so on. It's very often very useful to have also a free energy associated with this. Okay, so we compute Mi, but what is the energy of the system? Under consistent with our approximation, what is the free energy of the system? So this is a useful framework to combine approximations with the marginal to approximations on the free energy. Gives it many concepts. Okay, good. So let me take this formalism here, forget about the free energy now, and and go back to the Ising. Okay? The Ising model obeys this, so now apply it to the Ising model. And I'm going to make arbitrary Ising model. I'm going to make my life simple by taking fields to 0. So Hi external 0, which means that phi I is just 1. But it's easy to extend. All right, so under the Ising model, psi ij, all the si's are plus minus 1s, and the psi ij is just e to the beta jij psi ij. That's the only difference. Because si's are plus minus 1, introduce fields like MIJSJ, those messages, up to normalization. We can write them as e to the beta hij times fj. You can always write function which depends on plus minus 1 this way, and again after normalization. Okay, so now we have again cavity fields, but not total fields on J, but only the contribution from the neighbor I. Okay,
Well,
that's
previously you wrote MJI. Sorry.
okay. Good. Now, so we want to find these HIJs. Now, first of all, it would be nice to look here, relation between the total cavity field and this guy. So, PISI, I can always write as e to the beta, well, this is not the cavity, that's the full field, HISI, right? It's always the distribution. P of ISI is, that means that SI average is hyperbolic tangent HI by definition. You can always write them out again with normalization. So that's the definition of HIJ, that's the definition of HI. Okay. However, I can now plug here, this doesn't exist, I can plug in this relation. So then what we find from equation, write it as equation 1 and this equation 2. So from equation 1 we get that e to the beta HISI is e to the beta sum over j of h j not equal to I of h j I times SI from equation number 1. All right, so we can then conclude that equation 1 is equivalent to the equation that that HI, this field on the spin I, is simply sum over j, not equal to I, of the contributions, the cavity field HJI. Sum from all its neighbors.
These are the definitions of the
This
H's?
is what?
These are the definitions of the H's?
These are the definition of H's.
We find an H that...
Hij, that's the definition of this, and HI is that's the definition.
You still haven't shown that.
I didn't do it, I just introduced definition. This relation, this is definition. This is definition of Hij. And this is definition of HI. That's all what I did.
Yeah, but you get an equation that relates them.
This equation comes from equation 1.
Right, but you haven't shown that this definition fits the property of equation 1 because, right? I mean, when you wrote equation 1,
It's
you
the
said that...
definition. What do you mean? These definitions don't have any assumptions. I don't understand. I take Mij, Sj, I write it with e to the beta, and I take this, write it e to the beta, and compare. That's all. It's definition. There is no assumptions in those definitions. So
Then the question is if you need those to be the real probability. That's not necessarily the real
which probability?
What you wrote as PI is not necessarily the real.
Where?
PISI is not.
PISI is
Our approximation.
of course, I didn't say that this is a true thing. I wrote whatever this is a function of one Ising variable. Any function of one Ising variable has two values. And therefore it can always be written as e to the beta times something times Si. And then normalize it properly. always write mij as a function of it. It's just the fact that it's a function of a single binary variable of plus minus one. That's all. This is not. This is not. This is not any assumptions here. This is the definition of the hij and the hi. That's all. More questions about this?
So how do you know you can separate the probability, right? If you say the probability is a multiplication of mji.
Probability, you mean the normalization? What do you mean by probability? PISI has one number for SI plus 1 and another number of SI minus 1. It will be a probability if these two numbers are not negative and they are normalized. But since I made this, which means there is some normalization factor, and by construction this is always not negative, it's fine. It is always a probability. It may be the wrong probability, okay, but it is a probability. There's not much to do. You know, it has two values for SI plus 1 and plus minus 1. If they add to 1 and they are not negative, blah. So this is why there is no assumption.
But are we certain that we can sustain that equation 2 can
I didn't talk about equation 2. This is equation 1 in the language of the field. That's all. That's all. Good. Equation 2 now, as Tal said, is kind of more subtle, but it's still not such a big problem. Okay. Again, we just put e to the and so on. So what we have here, we have e to the j, e to the beta ji, beta h ji si. This is the left hand side times si, and then here there is sum of the of si plus minus 1. The sum is just two values, either si plus 1 or si minus 1. Fine, I don't care about this. Then there is e to the beta jij si fj. This is the psi. And then the product of the evidences going into j, but in the cavity construction. So this will be plus here sum over k, right, going into j. Sum over k, of course, not equal to j, but k also not equal to I. This is the cavity. The last inequality, the last requirement is the cavity requirement. That when I look at the evidence to Si, I have to remove Si from the game. Okay? And then I have this beta, so put beta here, plus beta h k j s j. These are the evidences going into Sj. Okay? This is now equation 2. I can finesse it a little bit, e to the beta h j I s I, and again, up to normalization. I can write it, so there will be some normalization. Let's write it some a for normalization. And then what will be here is two terms. One will be e to the beta jij s. I'm sorry, this is sj, right? Because I'm fixing si. Si with plus sj plus 1 plus beta. This term I can write down as hj because of this equation 1. However, there is an extra subtraction of minus hij, the cavity subtraction, and it comes with a plus sign because this is the term with sj plus 1. And then there will be another term here, plus e to the minus beta jij si minus hi minus hij. And these two terms multiply the normalization. So it's again very simple to solve. Why? Because there is again two values for Si plus 1 and for Si minus 1. And again, this will have two values for Si plus 1 and Si minus 1. Okay, for instance, you can take this with Si plus 1, subtract with Si with minus 1, divide by the sum, so then you can get rid of the A, and do the same here. Okay? And if you do it, you get, so again, you subtract the two values, plus 1 and minus 1, and divide by the sum of them. Then you get on the left-hand side hyperbolic tangent beta hji. And if you do the algebra, which I leave it as a homework and Gadi is in charge, is that you get product of hyperbolic tangent. You get hyperbolic tangent of beta jij times hyperbolic tangent of this cavity subtracted field. So finally, we get, this is what we called from equation 2, and then we supplement it by equation 1, which is written here, which is sum over j not equal to I of h j I. So these two essentially close our system.
We are missing the summation over J, maximum J and J.
Over j is fixed. Well, what is the sum of it? What do you mean j? J is the connection. So why should I sum of it?
Sum over J.
Just to make
No. This is ji. This is j. This is a particular contribution from j to I. So there is sum over. This is not sum over j. This is sum over the values of sj. This is marginalizing.
So maybe I need to.
If there is no sum over j, j is fixed.
Yeah. So maybe I need to conjugate the HJ in the HI on the right hand side.
Here,
Yes.
because this sum is from equation 1, is sum over hj, except that there is an extra subtraction. So this is why I'm subtracting.
But HJ. It's not HI.
Where? Here?
Equation 2.
I'm
There,
sorry,
yeah,
this
also
is,
there.
this is sum, I'm sorry, this is hj, thanks. This is hj. Okay, the sum of all this is hj, except that I'm subtracting the contribution from I to j. Right.
And then also.
And also here, thank you. All right. After the break, because I need to drink something, don't think about whiskey or something. Hey, Vysotsky. Okay, we'll try to think what does it mean. Okay?
מוזר בגלל שזה identity זה identity.
רגע, אני שנייה מתחבר מההתחלה של הבלגן.
הבלגן הזה.
כן.
לא, כדי לתת שעה עיקרית, רק מנסה להבין מה הדאטה. אחרי הרנדומיזציה, ואחרי
באמת?
זה לא ממש מופיע, חשבתי שזה יהיה
שם סינגולרי. חיים, חסר שם דאטה בארץ? נגיד שתבוא לשם.
אפשר לעיין אותו?
לא, לא.
טוב, שלא תהיה בשני השיעורים שבוע?
אנחנו נדבר על זה. שיעור אחד ביום שלישי בערב.
אוקיי.
ביום רביעי נדבר. מחר אחר הצהריים, בבוקר, של הפילוסופים. beta of hi. This is the definition of hi. Right? This hi is nothing but the definition of the log of p of hi. Okay, and then hi. The leaf propagation hi will be 1 over beta sum over j, not equal to I, um, of inverse hyperbolic tangent of the product of hyperbolic tangent of beta jij times hyperbolic tangent of beta of h, so there's some here, of ji, so it will be hj minus hij. These are the final equations for the marginal within this approximation. So this is very awkward. It's inverse hyperbolic tangent of this. Doesn't look like our usual Newtonian. Nevertheless, the claim is, and this is, we achieved something. The claim is that any Ising model on a tree, whatever the T structure is, these are the exact equations for the magnetization. Tree structure the particular tree structure, of course, will be into what Ji, which Ji enters, so this will be the geometry, but that's it. For any tree geometry, these are exact equations for the magnetization, without any further assumptions about Jij. Okay? So this will be exact on a beta lattice. Beta lattice is physicists call trees in two names. One is beta lattices, and another one is Cayley tree. And there's a lot of confusion in the literature. What are the difference between Cayley trees and beta lattices? So basically, one should say Cayley trees. The beta lattice is a Cayley tree, just a tree, right? Undirected tree.
It's
What?
regular.
No, there is no regularity. No, but beta lattice, maybe the definition of Cayley tree is regular.
I think so.
Okay, so then it's not even regular. It's tree. Beta lattice is okay. So okay, don't put them together. Beta, because this is true for any tree. Beta lattice is the limit of tree which is infinitely size. Kind of the thermodynamic thing. But very often you will find this as a beta approximation. This is exact on a tree, and and it's also called beta approximation. Again, beta lattice is a tree, but it has some infinite size of thermodynamic limit. Okay, good. Now, what is the connection between this and our mean field theory or our top equations or whatever, right? So first of all, look at this. This is not a simple, there is self-consistent calculation here because the h's are, and I didn't say what hij are. So there's another equation actually which I have to add, and this is that hij, or actually the equations are for hij, because once I know them, I know hi. So this is basically hjI. Okay, so I just wrote it like this and connected to mean field. So hij is what's written here is 1 over beta inverse hyperbolic tangent of hyperbolic tangent of beta jij times hyperbolic tangent of beta. This is now one term like this, so this will be h this is H, this is HJI, like HIJ.
Can we assume that Hij is symmetric if
No,
Jij?
I didn't assume symmetry here. No, but just the indices, but it's not symmetric. HIJ is not.
Yeah, but if
necessarily.
I'm asking if J is symmetric, does it mean that?
No, it does not mean, because the HI's enter, so you see that it's, there is here HI, so there is no symmetry between the role of I and J. Okay? So it depends on, on the heterogeneity, the structural heterogeneity of the system, the state of the system, and so on, whether it is symmetrical. Like when you generalize stuff, or random graph.
So if it's fully connected, then
Well, but the JIJs are different. The JIJs that the spin I sees is not the is not the neighborhood that the spin J sees. All right. It depends on the structure of the connection matrix, geometry, and so on.
Um,
Okay. Yes. More questions?
so that's same exact symmetry definition. You're saying that
What?
this is the same if the connectivity is weak, right? Because it's the exact symmetry and
No, I didn't assume any weak connectivity here. I assume
well, you use the tree approximation as a
the approximation is strictly valid is no loops, but not weak connection. This is exact on a tree for arbitrary
Right.
storm connection.
But you're still using it for general connectivity.
Okay, so now we'll come to it. Okay, so this is so far it is true for general. Well, it is exact for general tree for arbitrary storm connections. But now, as Meirav said, we can ask, okay, what happens if we are so this is a good approximation. Let's say not on a tree, but let's say random dilute graph. Then the presence of loops is very weak. The loops are weak, so you can say approximately locally it looks like a tree, and that's a very good approximation for those random dilute graphs. But what about highly connected or fully connected graph? Therefore, it's terrible unless now the connections are weak. So now we want to use this in another regime, not in the regime. So this is a good approximation for sparse graphs, random dilute, because the loops can be neglected. But we can ask also whether this is also a good approximation for fully connected or highly connected, but weak coupling. All right, so let's make this assumption. Let's make the assumption that the coupling is weak and see what happens to this equation. So if the coupling is weak, we now can say, forget about hyperbolic tangent and forget about the inverse hyperbolic tangent, just one. So then the beta drops. So then we get that HI is equal to sum over J, right, of Jij times hyperbolic tangent beta Hj minus Hij. And similarly, the second equation, again, what is Hij? Again, I'm going to make this approximation. So this is going to be Jij times hyperbolic tangent of beta of Hi minus Hji. So this is now, I'm now looking at the weak coupling. Yeah.
When you say weak, does that have a specific
So
name?
now there are two regimes. So when I say weak, so regime 1 or case 1 is Jij, kind of order of 1 over n. this hij. So hij also will be 1 over n. So there will be 1 over n coefficient to h, and this is not going to do anything to the field. So this will be just the naive mean field. And in this case, we just get that hi is simply sum over jij, hyperbolic tangent of beta hj, which is just mj. That's the naive mean field. Now the second scenario is that jij are the order of 1 over square root of n. Then the situation may be different because although this is small, but nevertheless it can be correlated with jij and altogether to give a contribution which is order 1. But we can argue the following. So this is going to be also of the order 1 over square root of n. So the hji here I can neglect. So then we get, in this case, we get hij is jij times mi. Oh no, sorry. Yeah, times hyperbolic tangent beta hi, which is mi. And then for hi, I'm going to substitute this. So this is going to be sum over j not equal to I of jij times mj. I'm going to expand to first order in hij. So then the second term will be minus sum over j not equal to I of jij times 1 minus j squared, the derivative of hyperbolic tangent, and then times beta, and then times jij mi. So finally we get that hi is sum over j mj, the naive mean field, minus beta times sum over jij squared times 1 minus mj squared, all this multiplied by mi. This is what? This is exactly top equation. In top equations, when we say, well, this is sum, this is j squared, and this is 1 minus q, but in general, it's a top equation. So what we got is, in general, from the perspective of the leaf propagation, if we take it to the weak coupling, we got the top equation.
It's only for the 1 over square root of n, meaning that
This is for what?
only for the second case, right? So the jij.
Well, for the first case, this is just 0. This is 1 over n squared and sum over n that is 0.
Yeah. So it shows you that the top equation is relevant only for the order of jij.
Well, we know that.
Sorry.
I mean, we said that yesterday, when it's 1 over n, then mean field, the mean field is exact.
Yeah.
Right, so that's another proof of that.
Okay.
Yeah.
What about correlation between J?
Correlation between them, so you will go back to the, you can compute similar inverse hyperbolic tangent and so on for the correlation by using marginal. This is a fantastic exercise. Compute correlation between SI and J. Compute equations for the SI, SJ, or the correlations, using the belief propagation, and see what happens when you go to the exercise. One more thing which I want to say about this is that because of my comments about top equations and about the free energy in this belief propagation approximation, which has to do with this, so we can actually write down also the top free energy. There are many ways of deriving it. That's not the only way of deriving it. But I just write it, the top free energy, which is a function of those MIs, is going to be, is equal to minus 1/2 the usual entropy plus P over 2 sum over I 1 plus mi log of 1 plus mi over 2 plus 1 minus mi log of 1 minus mi over 2. And then, but there is then correction, which is minus beta over 4 sum over ij, jij squared, 1 minus mj squared, 1 minus mi squared. And now if you take a derivative of the top free energy with respect to mi, you get the top equation. It's easy to see because this will give you inverse hyperbolic tangent of mi. The derivative of this will give you the naive mean field jij, mj, and the derivative of this will give you mi times the sum of jij squared 1 minus mk squared. So you get that top equation. So in that case, we can say that the top mean field equations for the magnetization has a free energy associated with it, which is the top free energy. All right. So now, as I promised you, everything seems fine. We got top equations from the Kennedy method. Then we get top equations from completely different thing from the belief propagation approximation. Of course, we got more than that because we got even in the strong coupling when loops can be neglected. But nevertheless, in the weak coupling, we got back to top equations. I want now to go back to the cavity method, to consider the Hopfield model. Okay? So this will be a nice exercise. Okay. Okay, we remember all this. So, cavity for Hopfield. Sounds like dentist. Okay. So let me remind you the Hamiltonian. It's the Ising model minus 1/2 fully connected J I J S I S J. But J I J are 1 over n times sum over P pattern contributions of P patterns, where you have the phi I mu, phi j mu, the phis are random, IID plus minus 1, that they will equal with equal probability. All right. So, let's do the top equation for this. I'm sorry, the cavity method. And
1 over n or 1 over n?
what?
1 over n.
1 over n. All right. So, okay, again, you probably have learned it. So if P is small, this is like usual mean field, J is order 1 over n. If P is order n, this will be order 1 over square root of n. So we are going kind of between the simple mean field to the kind of spin-glass specification. And we are interested in the case when P over n is alpha in order 1.
Hi.
Yeah.
Just the motivation is to compute the overlaps with the patterns.
To compute the mean field equations from the problem. Okay. Good. So we use cavity method, okay? So we already know what the answer is. Mi is hyperbolic tangent of beta h, the beta of we have seen that this is in general will be the structure of beta times sum over j, ji, j, and j, and then we have to subtract the vi beta times vi mi, and that vi came from the variance of the cavity field. So what is vi? Vi is delta h I squared average, again, cavity average. So this is going to be sum over j, sum over j prime, ji, j prime, and here we're going to have the correlation, the thermal correlation, cavity correlation between spin j and spin j prime. So far it went through the same as in the SK, there's nothing more. Assume the Gaussianity and the same story. Okay, now let's think about what should be VI. Okay. In the SK model, we said that these are cavity correlations, so they are uncorrelated with the J's, so then it's easy to see that only the diagonal term contribute, both diagonal cancel out. And then we get j squared times 1 minus q, and that's it. Okay, I'm sorry, okay.
But they are correlated with the J's are not
This is an
independent.
SK. In the SK,
Yeah.
those under the cavity, they don't know about this J. Okay? But now, we come to our problem. In the Hopfield model, this Jij, indeed, those guys don't know about the Xi's. But they do know about the Xj's. So they are correlated with the J's. Those correlation here, the J and J prime, okay, they don't know about the Xi's, right? Because Xi, here there is Xi, here there will be Xi, the site I doesn't exist, okay? But the problem is that Jij has also the Xj, the other things, right? The Xj, and they are correlated. Okay? So removing the node I with its pattern Xi doesn't really help us. Well, it help us so far, but doesn't really help us to approximate it by the Gaussian. Okay, so let's consider, let's write down what VI is. If we look at what VI is, it's beta times 1 over n squared times sum over mu and nu. If I plug in what the j's are, then there is Xi mu, Xi nu, then there is Xj mu, Xj nu, and then there is this delta Si, delta Sj under this cavity distribution. Okay, so it's easy to see that if I sum over the i's, I get the overlap of the fluctuations with the mu, and I get the overlap with the fluctuations with the j, right? So I'm sorry, there is here some, there is I'm sorry, vi, and there is sum over j and j prime. J prime, this is j prime, right? That's sum over j and j prime. So what we get is beta times sum over mu and nu times Xi mu, Xi nu, times the overlap of, times the correlation between overlap with mu and overlap with nu. Again, I'm okay. And now it turns out, again, one has to,
But how do you define mu?
this is the summation. This is just definition of delta m. Delta m is over.
After you sum over j.
I'm sorry, there is here sum over j and j prime. The summation over j and j prime. Now it turns out, again, you have to consider the correlations more carefully in Hopfield model. It turns out that the correlation of diagonal terms now of diagonal terms in the pattern space are negligible. Okay? And it turns out that this can be now written as sum over mu. The only contribution is from the diagonal term, then it's 1, ci squared is 1, and then you simply have delta m mu squared average. And now this is like our Q usually, so we can in the thermodynamic limit forget now about the cavity perturbation, and let's then call this beta times R, where R is defined as the sum over all fluctuations of overlap, thermal fluctuations of the state of the system with the square fluctuations with the overlap, with all the patterns. Okay, so that's beta R. So again, there are P of them, but each one of them is 1 over n. So altogether it's order 1. It's kind of alpha, P of n. Okay, so this is something of order 1. All right, so now in business. So now put it back into our equations. So then we get mi equals to hyperbolic tangent, beta, sum over j, mj, minus, now we get beta r times sum mi, instead of j squared 1 minus q.
So replace two consistent equations within one because defined both by the mean and the fluctuation.
By the what?
By the mean and the fluctuation. So m
Yeah,
has
no,
to be.
the fact that it's random fluctuation is here, right? Because of the Gaussianity of the cavity field. But the difference between this and the Hopfield, or the SK model, that the variance has a different shape. That's the difference. It's still a cavity field here times mi, but this has different shape.
Yeah.
Okay, good. So now what we have to do, we have to compute R.
Right, if you do it with the n.
No, that's a problem now, because this is fluctuations around mean field. I cannot compute it from here. Well, not in a simple way. Okay? So how do I do R? Okay, that's now the question. So we can work hard. Let me tell you what we did, but it's not the only way to do it. Me, Maoz Shamir, this was part of his PhD in the paper in 2000. Actually, it was a problem for several years because people just use path equations and then found that you don't get the right mean field. Turns out that it's not the right thing to do. Now, how do we compute R? So, here's it. It was a brilliant idea, okay? Now we do cavity and pattern space. What we want is a distribution of this fluctuation, right? And the way then what we do okay, so what we do there is to compute the probability of this overlap. So we want the probability of these small overlaps, this delta mu, these probabilities we want. The residual probability, the marginal probability over one of these n's. That's what we want. And because these n's are small, then it again, Gaussianity and so on, but we need to do cavity.
And it can depend on you, or
The probability will not depend on you, and will not depend on you, and actually what we end up is, as I said, cavity in the pattern. So we now remove the pattern and compute the probability of the remaining pattern, the fluctuations, and then add it again, and okay, so what we get is P of M of the let's call it pattern 0 under the P plus 1, the full system, is up to normalization e to the 1/2 beta n times delta n squared times P of the P patterns of delta n0 or n0. Delta n, if there's a macroscopic condensation, then like it. So basically, we get basically Gaussian approximation for delta m, where this is kind of updating of the variant by this equation. Okay, and if you then solve it, you get that the delta m0 squared average, the full one, is 1 over n times 1 minus q times 1 minus beta 1 minus q, and this is basically 1 over n times r, right? Because r is sum of this, many of these terms. So this will be alpha r, right? If I put alpha here, then it will be per pattern. So R will be the mean fluctuations of a single pattern. Or maybe that's where I could put here 1 over n. Yeah, then it's alpha. Right, so I put here 1 over n and P, then there is alpha. So put this there, then it's alpha r, right? So it's here. Or the opposite, if I have R there and I put it here, that's the right thing to do, R here, and then it's alpha r. Alright, and that turns out to be the right mean field. In what sense? In the sense that if you put this R here from this equation, then it's connected to Q, so I get R equal for alpha R, sorry. No, yeah. Opposite.
and or
R is alpha. So for that, then you get R equals to alpha of 1 minus Q divided by 1 minus beta, 1 minus Q, and Q is the usual thing, it's the Gaussian mi squared average. Okay, so
So this would only work in that regime of alpha also?
in which regime?
In the regime of alpha.
Otherwise, the amazing couldn't work.
Yeah.
So there is no problem. Okay, so you can see the details in the paper, but it's interesting. Why? Because it seems that the cavity method not necessarily gives you the same type equations as the belief propagation. I leave it as an open thing, because in belief propagation we didn't make any Gaussianity and VI and so on. We just expanded in J, and then we got our equations, which are the usual type equations. Okay? Here, the assumptions of reconnection, recoupling is correct, because this is almost 1 over square root of n. Nevertheless, the type equation by the cavity method, if you do it carefully, it is the correct equations, not the belief propagation equation. So, what is the take-home message? propagation equation, which leads in the weak limit to the naive type equations, where you have just the simple term. As I said, it's either, I mean, it relies on having weak contributions from loops, okay? For the S case, it's true, okay, although there are loops, but the JIJ are weak, but not enough. It's also true that when you take a loop and you look at the product of all the J's along the loop, they kind of cancel each other, the contributions. On the other hand, in the Hopkin model, they will not, because of this cancellation, because of Ci, Cj, and then Cj, Cj prime, and so on. So there are strong correlations along a closed loop. And therefore, the loops, even though the J's are weak, the loops have a more substantial role than the SK model. And that already shows you how the whole thing of rushing and taking some approximation can be dangerous. Okay? You really have to understand about the system and more in order to adopt one approximation over the other. So I would argue that when you have weak connections, fully connected weak connections of the order of 1 over square root of n, that they are not kind of independent like the SK model, but they have some sort of complicated something, then the cavity method is the correct way to go about it, and not the naive thing which you get from the naive type equations where you have simply J and J squared times 1 minus theta or something like that. So I can close it by asking, if this is so, let's take a general system with full connection and weak coupling, order 1 over square root of n, but I don't know more than that. There are some strong correlations. Imagine that it has this plus some J and J plus Ci, Cj, Cj, well, J, Ck. Okay. But anyway, you understand the point. There are some correlations among the J's, although they are weak. Okay, what can we say about the mean field? Okay, we have done a lot. We have done a lot. We have reached this point. So I would argue that these equations are fine with this. So these equations up to here are fine, because the weakness give rise to Gaussianity. Fine, we got to here. So the main problem that we have is to take this equation and to apply it to some complicated system is to compute VI. The problem is that VI has this fluctuation, pairwise correlations, and it's not part of the MI fluctuations. So what do we do in general with this? So here we were ingenious, we took a pattern, we did cavity in the pattern to get this. But in general, I don't know what to do, what to pull out in the system. So here is a general recipe. A general cavity equations, general type equations, but not the naive type. Okay, what do? I have everything, but I have to know what to put for delta Sj, delta Sj prime. What to put within the mean field theory. Okay. So now I recall that at some point, Heinz Sobolewski taught us the statistical mechanics course and told us that there is a fluctuation dissipation theorem that says that this, well, there's beta there, is beta. This times beta is nothing but the susceptibility matrix chi j j prime. What is the susceptibility? Is taking the derivative of m J with respect to some external field, small, I'm sorry, J prime, respect to, or J with respect to a field J prime, doesn't matter, it's a symmetric matrix. This is nice, because I can add fields to the mean field equation and compute susceptibility measure. I cannot compute directly fluctuations because there are no fluctuations, but I can compute susceptibility. So let's do it. some approximation here. Okay, you are right in principle, but okay, let's see. There will be some approximation. So let's add this small field into this equation. Sum over j, jij minus beta, I'm sorry, mj minus beta vi mi, and then plus some little hi0, some small field. Now we take a derivative with respect to some field j0, hj0. Okay, we take a derivative, we get 1 minus mi squared. Then we get beta times sum over j, jij. The derivative of this is j prime, chi j prime j. We're taking the derivative of the n's. Then we get from delta hi0, of course, we get that delta ij. Delta ij. This is the source term. So we get this. And then we get this cavity thing. So we get minus beta vi times chi I j. So we can, we can just solve for chi. We can write chi, the matrix chi is the inverse of A minus J, where A is Aij is diagonal matrix with the 1 minus mi squared inverse plus vi in the diagonal. You can just rearranging, putting here in inverting the matrix. So we have chi. Okay, so now we can self-consist for the chi that we're missing here. Okay, and then kind of complete the entire thing. Comes Manfred Otter and Winter and come up with a brilliant idea. You don't actually have to use this equation at all. Let's think about VI's unknowns. Okay. What do we know from this system? Well, we don't know chi. Chi now is a function of these unknown variables VI, right? And of course MI also. However, these are their brilliant idea. However, we know something. In the Ising model at least, we know what the diagonal elements are. Because chi I has to be equal to beta times 1 minus mi squared in Ising system. So we can write down n equations, which is that the A minus J inverse II, the ith element of this matrix, have to be equal to this. So we have n equations for n unknowns VI. Self-consistent equation. So we don't have to use this. We forget about this. Think about VI as cavity corrections, which we don't know what they are. Okay? But through the computation of the susceptibility and the self-consistently that the diagonal